We're building a hardware wallet for dApp operators. Check it out. Okay, so let's look at an example here with a fictional dApp. So in the bottom right, we have our hardware wallet attached to the server backend in the top right. And on the left side, we have our user-facing front end. So as a user, let's come in and purchase 1,000 tokens. So I will sign that transaction off screen. Eternal, okay, we're submitted. So let's check it in Eternal. So once this transaction is submitted to the blockchain, on the right side we will see our server backend pick up that transaction. It'll calculate how many tokens the user should get, build that transaction body, and then send that to the hardware wallet to sign securely. That hardware wallet will then send the signed transaction back to the backend to submit to the blockchain. So we saw that just went through, and here the backend picks it up. It's submitting it to the hardware wallet. Here we got the signed transaction back and submitted to the blockchain. And then here in a second on the left side, we will see those tokens show back up in our wallet. So let's wait a quick second. And there we go. 1,000 tokens came in. So brief example of how a dApp operator can use this to secure the private keys for, in this instance, minting a utility token for the dApp, securing that in hardware. Okay, so let's dig into the technical details of our hardware wallet design. Everything is open source in our GitLab repository, and we have several readmes that dig into various technical aspects of the project. So the key enabling technology here is the ability to autonomously sign transactions from the hardware device, which allows it to be integrated with a live dApp service. The secure enclave in the device provides cryptographically secure management and the ability to sign transactions using those wallet keys, and this is enabled through ARM Trust Zone. Additionally, we are working on a configurable TX guard that allows you to write application-specific code to filter out transactions that look abnormal to your specific service. So if an adversary gets into your server and generates a transaction to drain the wallet, you can throw it away. If they generate 10,000 transactions in 10 minutes, you can throw those away. And additionally, we have a physical layer firewall that prevents exploits via the serial interface. So we only allow CBOR serializable transactions to be sent through, not arbitrary strings of bytes. So let's take a quick step back and talk about what exactly is a hardware wallet. Hardware wallet is a device that combines a microcontroller with some form of secure compute element where the private keys are securely handled. So you have a serial interface that is the communication protocol between the host PC and the device itself, and you have a pin lock that prevents local attacks on the device. And then by nature of it being a microcontroller, being a limited device, not running an operating system, there's security and the simplicity against side channel attacks on the hardware itself. So how is our device different? So this block diagram here will look very similar, except we've inserted a Linux CPU here in the middle. So we still have this basic microcontroller in the front that serves as our physical layer firewall. It prevents you getting shell access from the PC into this Linux CPU. So in here we have our first layer of defense. We are analyzing the data that comes across the serial interface and will only allow valid CBOR transactions to go through the microcontroller into the Linux CPU. Additionally, we also have a pin lock. This is only provided on power up when you plug in the device to prevent local attacks on the hardware. And then we will be inserting our configurable transaction guard into the Linux CPU. Finally, valid transactions get passed on to the secure enclave to be signed and passed back to the host PC. So why should you use this on a server versus a hot wallet? So billions of dollars have been lost in hacks just through leaking wallet keys. When you leak a key, it's permanently compromised. There's no getting that back. Once an adversary has your key, they can mint arbitrary transactions. They can wreck your token. They can steal your funds. So protecting those private keys is paramount and can really limit the scope of the damage an attack can incur if an adversary gets in your system. So let's look at a high-level sequence diagram of how this works. So you'll have a host PC or a server. build a transaction, and then you submit that transaction CBOR to the device. So as we talked about, it goes through the microcontroller, through the firewall, only allowed through if it's a valid CBOR string, then passed on to the Linux CPU, where the customizable guard can filter transaction contents that look abnormal, and then finally gets passed on to the secure enclave, the ARM Trust Zone trusted execution environment, to sign the transaction and then pass that all the way back to the PC to submit to the blockchain. So our first prototype is based around a development board. This is from ST Microelectronics, and it's the MP157F Discovery Kit. So key features here: it's a system on a chip that incorporates a dual-core ARM Cortex-A7 CPU and then an ARM Cortex-M4 microcontroller into a single device, along with some DDR. This device possesses ARM Trust Zone, which is our secure execution context. This is where we're securely managing wallet keys. The CPU runs OpenST Linux, which is an embedded Linux distribution provided by the hardware vendor, and it has a nice 4-inch touchscreen display for some good information about what's happening on the device. So just a quick overview how Trust Zone works. So within the Cortex-A7 CPU, you have the non-secure environment and you have the secure environment. So non-secure environment runs the Linux operating system, runs user applications, and has a API library that allows you to securely pass data back and forth to the secure environment. In the secure environment, this runs what's called OPT, a trusted execution environment. It runs trusted application code where you can securely handle wallet keys with no risk of them being leaked outside of that secure environment. So let's just briefly dig into some key pieces of the embedded software we developed. We're not going to dig into everything. There's a lot here. Just want to touch on the highlights. So first, we'll touch on that microcontroller. So what that's doing is it has two serial interfaces. It has a physical UART interface to the host PC, and then it has a virtual UART interface where it passes data from the microcontroller through that system on a chip into the embedded CPU. So first up here, we have an interrupt service routine that gets called every time a byte is received from the host PC. And all we're doing is putting it in a buffer and then kicking off a timer. What we're doing is looking for the end of a complete message. So you send a full transaction CBOR string. We stick those bytes one by one into a buffer, and then when we've gone 500 milliseconds without getting another byte, we call that the end of a message, and that triggers the second interrupt service routine where we take that buffer, we check the CBOR. If it's valid, then we send that over the virtual UART to the host PC. And then we scroll back up here real quick. The main function does the same thing in reverse. So we're checking through, it's called OpenAMP RP message. That's what our virtual UART to the CPU looks like. We check for a new message, which would be a signed transaction coming back. If we see that come in, we pass it back to the PC. Pretty simple. Okay, now let's jump to the ARM CPU. So this runs a main routine that is waiting for a transaction string from the microcontroller. When you receive that, we do some basic filtering here. We don't yet have the TX guard implemented. So here we just look for buffer being above 10 bytes to start with. Make sure it's a CBOR string. And then we're going to compute the transaction ID from that string. So the way you do that is you look at the full transaction body in CBOR, and you compute the Blake2B hash of that body, and that is how you get a transaction ID. You take that and you pass that to the trusted execution environment to actually do the secure signing. So here in the sign transaction function is where we set that up. So how this works is you initialize a context to the trusted execution environment. You set up the buffers for the input and the output to that secure environment. So we set up a buffer for the TXID as the input, and then we allocate space for the transaction signature to come back. And then we just invoke the command to sign a transaction, and that will kick off the trusted application in the ARM trust zone environment to sign the transaction. So on the reverse side, we have the params that we sent in. So we have the transaction ID buffer input, and then we're set up to provide that signature back. So one thing to note here, this first milestone of our Catalyst project, we've just hard-coded in the private keys. While this is secure, the key is securely in the trusted application. It can't leave. This is obviously not the ideal way to handle wallet keys. You don't want to have to compile that into the code. Milestone 2 would be devoted to securely handling those keys and being able to generate arbitrary keys in the device. So for now, we just have that hard-coded here. And then all we do, pretty basic here, is we call Cardano Crypto ed25519 sign. That's the signing algorithm that Cardano uses. We ported that algorithm in the SHA-512 algorithm to run in this trusted application on the embedded device. It computes a signature based on the transaction ID and passes it back to the CPU. So again, let's look at that sequence diagram again and see what we step through. We're building a transaction on the PC, passing it to the microcontroller, receiving it on the UART interface, checking if it's valid CBOR, sending that onto the CPU, all the way through to the trust zone, and then sending it back to the host PC. So look around our repo, reach out to us if you have questions, let us know what you think, and if you're interested in using the device, we would love to chat. So thanks for watching. We'll catch you next time.